I'm Naomi Wells.
I'm Trevor.
I'm Brooks Montoya, and for our project 2 here, we're going to be working on buoyancy.
We're going to be finding out why certain things float and sink in both air and liquid. Like, why does rock sink?
Okay, what is a buoyant force? It's the upward force exerted on an object immersed in fluid or in a gas, like balloons or.
Alright, so this is going to be our model for the buoyancy force. Now, overall, in relation to other concepts we've learned in Physics 212 so far, the buoyancy force here doesn't necessarily relate to anything rotationally or frequency-wise. But what it does relate to are the analysis methods we've learned throughout this course and even Physics 211. Seeing as here with our extended free body diagram, we can use this to demonstrate and explain how the buoyancy force works. Now, in this example, we have an ice cube and a glass of water. And the way the buoyancy force works is you have your gravitational force acting on the object, pushing the object downwards. The weight of the object, which in combination with the gravitational force, is all that combined, pushing the object downward. Then you also have the buoyancy force, which is pushing the object upward. Now in this case, the ice cube, it's sort of a neutral object, so it's half in, half out of the water. And then the final part of our equation here is just the P fluid. Okay, so the formula for the buoyancy force here is equal to the buoyancy force is equal to the density of the fluid times the gravitational force times the total of the fluid volume. Now there are 3 cases for buoyancy. The first being when it's neutral, as seen as the ice cube here, where the force of gravity is equal to the buoyancy force, in which an object's floating, sort of half floating, half sinking in a way. The second case is when it's negative, in which case the force of gravity is greater than the force of buoyancy, which is, when the object sinks, like a rock. And the final case is when the buoyancy force is positive and you get a force of gravity is less than the buoyancy force, in which case the object completely floats on the surface. So the first case of buoyancy we're going to be taking a look at is when we have positive buoyancy. And this means that the immersed object is lighter than the fluid displaced. So we take a look at our diagram here. We have a cork, which is floating entirely on top of the water, which shows that it has positive buoyancy. Now we know it has positive buoyancy because the force of buoyancy here completely overpowers the force of gravity on the cork, meaning that, as I said, force of buoyancy greater than the force of the cork, which means the cork is floating entirely on top of the water.
Neutral buoyancy is where the immersed object's weight is equal to the density of the fluid that is displaced, displayed most commonly in driftwood. It's where half of the object is submerged under the water and the other half is above the water, making sure that the force of gravity on the wood or other object is equal to that of the force of buoyancy. It's also common in icebergs.
Our third case of buoyancy is negative buoyancy, and this happens when an immersed object is denser than the fluid it's displacing. This can mathematically be shown by the gravitational force on the object being greater than the buoyant force. An example of this is when you put a rock in water. The gravitational force on the rock is greater than the buoyant force pushing back, and we end up with rock sink.
Wow.
Okay, so another good example of buoyancy is comparing a steel boat to steel rebar. Steel boats are designed to float on water due to the ability of displacing a larger volume of water, as well as in their design they are designed to include water and air into the density of the boat. So instead of just being a giant brick of metal floating on water, it's a combination of things creating its density. Whereas steel bars and rocks are solid pieces of metal or solid objects that have compacted density, and so in turn the force of gravity on rebar is larger than that of the force of buoyancy, so it'll sink. Whereas the boat, regardless of its size and mass on land, the force of gravity is equal to that of the force of buoyancy due to its composition. So then you're not worrying about your gigantic boat sinking, whereas you could drop rebar into the ocean and lose it.
All right, so to go over the formula we just discussed for the buoyancy force, we know that it's equal to negative density times the force of gravity times the total volume of the container. As we can see here, the formula for density is equal to mass over volume. Gravity, we all know, is equal to negative 9.8 meters per second squared. And from that, we can set that equal to actually the net force on the object, which is just ma. So set those equal to each other. Gravity cancels out here. Then moving on to this line, we end up with just the mass is equal times the density times volume. We can isolate density of the liquid right there, set that equal, which results in, we get a number m over v, which as shown here is once again just the formula for density. So now we end up with this equation that in a scenario where the buoyancy force is active, that the negative density of the object is equal to the density of the liquid and vice versa. Now from this we can start doing on our sense-making topics and carrying on with different scenarios to see how this affects it.
Based on our previous derivation of the buoyancy formula, we found that the two most important things are the density of the object and the liquid. What this means is that we don't actually have to calculate the buoyancy force and the force of gravity on the object to see whether the object is buoyant or floats. We can see if, or we know if an object is floating if the density of the object is less than the density of the liquid. And then we know if an object will sink if the density of the object is greater than the density of the liquid. A really weird and cool example of this is mercury in an anvil. Mercury is super dense, so when you put an anvil on it, it actually floats. Mercury's density is 13,000 kilograms per meters cubed, and an anvil's is only about 7,900. And going off that, whether an object, like which is greater between the densities, we see that based off that, the anvil should float, and it does. We found a really cool video online that showed that.
Let's set it in here and see if it floats. Okay, it doesn't seem to want to stay upright. I'll just let it tip over. There it is. It's floating. Look at that. The iron anvil floats because mercury has a density nearly twice that of iron. In fact, due to the density ratios, the iron actually floats better than wood does in water.
Push it under.
Let's push it down. Oh, that's hard to push down. Oh, that's great. Here, let's try it again from the other side. Okay, here we go. Push down.
So like liquid, there are different densities of air and gases. Helium is an example of a very light gas, whereas normal air is, just normal air. Still lighter than most objects, including feathers. It just allows for it to be less forceful when going downward. And then there's things like sulfur hexafluoride, where Mythbusters actually did a bit on it, where you have feathers on top of the gas inside of a tub and it'll float. Because sulfur hexafluoride's density is so much thicker than that of normal air, as you can see here. But an only way of really conceptualizing, I guess, having a feather in a bucket of helium can be represented with balloons, because if you release a balloon full of helium into the atmosphere, it'll float. And if you fill a balloon with sulfur hexafluoride, it will sink to the ground. So, as an extreme off of going through an anvil floating on mercury, we decided to include something funny I did, which is an alternator versus the density of air. As you can see here, an alternator is roughly 6,000 kilogram meters cubed. This is roughly if it was a complete solid mass, which they are not, versus air, where the density is 1.225 kilogram meters cubed. Hilariously, a friend and I got to replace an alternator, and we decided to just huck it into a bush. And so we've decided that that is a good representation of something very dense going through something very not dense, like water or air. I'm assuming if we did do it versus mercury, it would also float, since it is roughly the same density as an anvil over such a wide area versus anything else.
Overall, I felt that when we were creating our model and making sense of our buoyancy, we only needed to incorporate two concepts that we have learned. The two concepts that we have learned that we need to incorporate are Newton's second law and extended free body diagrams. We use free body diagrams to show how the force of buoyancy works against gravity and how objects are able to float, sink, or be in the middle in that neutral buoyancy. We use Newton's second law to simplify this equation into where we only need density and just make it a lot easier to work with. I felt that overall, buoyancy didn't really use that many ideas and concepts from this year, Physics 212, but used more of concepts from physics.
Alright, so in conclusion, why does the rock sink? Well, it comes down to mainly the density of the rock versus the density of water. Density of the rock clearly heavier than the density of water, which means that rock's going to sink to the bottom, which in turn affects the buoyancy force of the rock, meaning that it's greater than the buoyancy force of the water, so therefore the rock sinks.